Good day. Welcome to part 3 of the presentation. Is there a power of 6 that starts with a 9? Let's go over the outline of this third and last part. First, in this case, we will introduce the idea of frequencies of appearances of 9 as a first digit in powers of 6. So, not only the fact that we have infinitely many times, but what is the frequency? We'll talk about that. Then we will introduce the notion of uniform distribution and Weyl's theorem. Finally, we will talk about some topics that you may be interested once you finish the real analysis course and start learning measure theory and you want to explore a little bit more. We will talk briefly about ergodic transformations and the ergodic theorem. And we will see the connection of Benford's law with the discussion of first digits in powers of 6. So the notion of frequencies. First, we will explore what does it mean for a sequence of integers to have a frequency. For example, if you think about the even numbers, if you look at the first 1,000 even numbers, half of them will be even. And you look at the first n numbers, about half will be even. So we'll say that the even numbers well-defined frequency, and its frequency is 1/2. Not every sequence of integers has to have its frequency, but in the case of the even numbers, they have a frequency. Multiples of 10, for example, they have a frequency, and its frequency would be 1/10. So let's look at this in more detail. We're going to use something called the indicator function of a set. The indicator function of a set I sub a is a function so that at x is equal to 1 when x is in A, and it is 0 when x is not in A. So we think of this I sub a of x, indicator function of A. It tells us when x is in A or not. Okay? So for example, if you look at the sum, we say the sum from 0 to n of the indicator function of the interval log 9, 1 of t to the I of 0. What does it do is count the number of times t to the I of 0 is in the interval log 9, 1 for I starting at 0 to n. So that sum is counted the number of times the orbit of 0 visits the interval log 9, 1 and the iteration by t. Okay? So the frequency then of appearances of 9 as first digits in powers of 6 will be this limit if this limit existed. You divide that by the number of integers you have seen. From 0 to n, you have n plus 1 integers. So you look at 1 over n plus 1, the sum from 0 to n of the indicator function of log 9, 1, evaluated at t to the I of x. I is going from 0 to n. Okay. If that limit existed, this limit is the frequency of appearances of 9 as a first digit in powers of 6. So we have this notion of a frequency of appearances, or frequency of a sequence of numbers. Well, now Weyl's theorem is a theorem in real analysis, but can also be considered as the first theorem in a subject that we will mention later called ergodic theory. Ergodic is not an English word, but it's a word that was invented to describe this subject. So Weyl's theorem on uniform distribution says the following. If n alpha bracket, parenthesis, denotes n alpha modulo 1, then if you look at for any interval I, the frequency of appearance of n alpha in I is equal to the length of I. So n alpha, another way of saying, is uniformly distributed in the unit interval. This is when alpha is an irrational number. For every irrational number alpha, that's very crucial. That is not clearly denoted there, but this is only for alphas which are irrational. We've already earlier talked about the distinction between rational and irrational. So if alpha is irrational, and if you look at n alpha, for example, we explore n log 6, and log 6 is irrational, log base 10. N alpha is uniformly distributed. If you look at it, it will visit an interval of length 1/10, a tenth of the time. It visits an interval of length 1/1,000,000, a million of the time. And visits all the intervals in 0, 1 uniformly, just depending on the length. So this is the content of Weil's uniform distribution theorem. We're not going to prove that this time. This is something that you could look forward to another presentation where you could see a proof of this theorem. But it's a very beautiful and interesting theorem about uniform distribution in the unit interval. Well, it turns out that n alpha for alpha equal to log 6 is t to the n of 0. Is what we wanted to know. And so this is telling us that the powers of 6, 9 appearing as a first digit in powers of 6 has frequency equal to the length of the interval log 9, 1. And the length of that interval is 1 minus log 9, which is approximately 0.0457. So we will say that the frequency of initial 9s in powers of 6 is about 4.58%. We will see that's the frequency of appearances of 9 as first digits in powers of 6. So we see that here as a consequence of Weil's theorem on uniform distribution. We can also ask about frequency of initial 2s. What does it mean that 6 to the n, the first digit in 6 to the n is 2? That means that 6 to the n will be between 2 times 10 to the k and 3 times 10 to the k. You take logs on both sides and you see that that has to do with the orbit of 0 visiting the interval log 2, log 3. Visiting the interval log 2, log 3. So by Weil's theorem, the frequency of appearances of 2 in powers of 6 will be the length of the interval log 2, log 3. And that gives you that the frequency is approximately 17.6%. Sometimes people think of that as 18%. Similarly, one can see that appearances of 1, the frequency of appearance of 1 happens to be 30%, which is given by the length of the interval from log 1, which is 0, log 2. The interval from 0 to log 2, and log 2, that interval has length log 2, which is about 0.30, log 2 base 10. Now, let's make an interesting remark. If you think about frequencies, if you were to just look at in this table, for example, if you look at powers of 6 and you look at it from 1 to 175, you don't see 9s. For example, the frequency would for 9s, and you see, or you can count the other numbers. But initially, if you just look at up to 175, you will not see appearances that go to the limit that is given by Weil's theorem. If you take larger n's, say up to 175 times 10 to the third, you will see the frequencies that we were talking about. You see frequencies 1 already 30%, frequencies of 9, 5.8%. Turns out those numbers, those frequencies, happen to also be what are called the Benford's frequencies or Benford's law. Benford's law is a statement that many naturally occurring numbers, such as street addresses, housing prices, and initially it was observed in logarithmic tables. If you look at the first digits in those numbers, they obey the frequency distribution that follows from first digits in powers of 6, follows from Weil's theorem. And it is a surprising fact because sometimes people would expect that the frequency would be the same as the first digits, that all the first digits will be uniformly the way you would expect. You don't see 0 as a first digit, you would see 1 up to 9, so about 1/9 of the time. But no, 1 appears at a higher frequency than 9. So the last part of the presentation, we're going to change this a bit, and we will talk about how Weil's theorem follows from the ergodic theorem. So this is just to get you interested about new topics as you continue your studies in real analysis and start looking at measure theory. Eventually you will meet a very important theorem called the ergodic theorem. And the ergodic theorem is a very general theorem about frequencies, and it implies Weyl's theorem. That's one way, not the only way that one can prove Weyl's theorem. Weyl's theorem was in fact shown before the ergodic theorem, but one can see that theorem now as a consequence of the ergodic theorem. The ergodic theorem applies to what are ergodic transformations. So let me just talk about them briefly. A transformation such as T is said to be ergodic if it has no invariant sets other than the obvious ones, other than the sets of measure zero or full measure. Now, to properly describe ergodic transformations, we need the notion of measure, and here we're just thinking about lightly. You can think about a probability. The length of an interval, the measure of an interval is its length, and the measure zero would be essentially, you can think about probability zero. So if you have an ergodic transformation, it will satisfy the ergodic theorem, which says that average, the limit as n goes to infinity of 1 over n, sum from 0 to n minus 1 of the characteristic, the indicator function of a at t of I of x, goes to the measure of that set. And then when the set A is an interval, its measure will be its length. And the ergodic theorem here needs that this transformation has to preserve the measure, which our translations do, and needs to be ergodic. It turns out that for our case, t of x equals x plus alpha, that happens to be a measure preserving an ergodic transformation. Intervals are sent to intervals of the same length, and it is ergodic when alpha is irrational, and the proof of ergodicity uses Kroneker's theorem. One can prove ergodicity using Kroneker's theorem. So by the ergodic theorem, it will follow that those averages, which will be frequencies, will be the measure of the set, which is the length of the interval, and in particular implies Weyl's theorem. So this last part just has been here to give you an idea of things to come. If you continue your studies in real analysis, you will see measure theory and ergodic theorem, and you will see this other theorem that implies Weyl's theorem. To finish, let me just say we have discussed an interesting question that brought us to a lot of topics: transformations, the notion of density, Kroneker's theorem, the proof of Kroneker's theorem, and then further notions in real analysis. So let me leave you now with a question as we end this part, the last part of our presentation. We have seen that there exist infinitely many powers of 6, and in particular any powers of 2, since log 2 is irrational. We know that there exist infinitely many powers of 2 that starts with a 9. There exist infinitely many powers of 3 that start with a 9. So the question now is there an n so that both 2 to the n and 3 to the n, that is for the same n at the same time, they both start with a 9? How would you show that? So that's a challenge question that I leave you with. And this concludes our presentation on first digits of powers of 6.